Hello and welcome back to Differential Equations, section 4.2. We're finally going to see how to transform the differential equation using Laplace transform. Now, differential equation is defined that any equation that has function, its derivatives and variables around, is a differential equation. So we are not only transforming functions, we are also transforming the derivatives. And we need to learn how to transform derivatives first and then deal with the equations once we know how to do that. So we start by Theorem One. Suppose that the function f of t continuous and piecewise smooth and for t larger than 0 and is of the exponential order as t goes to positive infinity. So there exists a non-negative constant m c and t such that f of t is bounded by this, then the derivative. So you can actually prove this derivative by writing out the integral and then working it out. I am only giving you the formula, which you have to memorize, because this is how you differentiate, this is how you transform the first derivative, and then you will remember the one for the second derivative, and then just use them. Now, if you are interested in how to obtain these formulas, you are going to work out the integral, and it works just fine. So, Laplace transform of the derivative of f of t is going to be s times the Laplace transform of f of t minus f of 0. Now we know that this is s f of s minus f computed at 0. This gets a tick box. I'm going to point out here immediately, right? You see that green thing that I circled? That's your initial condition, okay? So now, in purple, initial condition. So the question is, can you do these differential equations if you don't have the initial condition? And the answer is no, you can't. You can't do them. Because you see that the initial condition plugs directly into the derivative formula. Great. So now, the second derivative is equal to s squared Laplace transform of f of t minus s f of 0 minus f prime at 0, which can also be written as s squared f of s minus s f of 0 minus f prime of 0. Also gets a tick box because you are going to use this a lot. Now, in general, right, and some of you might want to learn just the general case. In general, you have, or maybe I should also point out before I do that, so initial conditions. Second order better have two initial conditions. So you have spots where to plug them in. So now in general, now this is if you see the third derivative, fourth derivative in a differential equation and so on. So in general, Laplace transform of the function to the nth derivative, remember the notation, right? It's the n in parentheses. So if you need the seventh derivative, right, the derivative is like that. So we have Sn, s to the n, right, which is the order of the derivative, times the Laplace transform of f of t, and then minus, and now you start subtracting, so Sn minus 1 times f of 0 minus s to n minus 2 times f prime of 0 minus, and this goes forever. So I'm going to cut it here and go minus s fn minus 2 computed at 0 and minus f of n minus 1 of 0. Now this is not what this is not. This is this is the general case, and you can deal with the seventh derivative or the whatever, right? Now generally we use first and a second derivative for differential equations, so knowing the two formulas above is sufficient, but you can replace those two formulas completely with this one boxed in red. Yes?
Over by the corner, right corner.
This is a prime over here. Just like, oh, you can't see it here because I put these arrows and stuff. There's a prime right there. Right, there's a prime here. See that? And that's the same prime that's here.
So it's Sn minus.
What happened? Well, oh, this. I hope I put these parentheses here because these are derivative orders. Solve the initial value problem. So let's transform this stuff. Solve initial value problem. It's called IVP, initial value problem. And I don't want to do the one that's in the book because So here's number 4. X double prime plus 8x prime plus 15x equals to 0. X of 0 is 2. And x prime of 0 is 3. Now I said something last time, I don't know if it's stuck or not, but the purpose of Laplace transform is to change the differential equation you have into basic algebraic equation, and then you manipulate that using basic algebra and basic arithmetic, and then you use the inverse Laplace to bring it back into the what we call time domain, right? Bring it back to the original variables, original problem, to get a solution. And in the whole process, you don't do any derivatives or integrals. You just do basic algebra, which is the reason why this method was preferred and beloved by all engineers before computers and calculators and other stuff came about. So solve initial value problem. I need to transform x double prime. Well, we know what that is. It is s squared f of s minus s times the initial condition, which is times 2, and minus another initial condition, which is 3. So all of that is this. And then I have plus 8 times, and now I have the first derivative, which is s f of s minus, and now I get to use just 2, because it is right? So I use this formula right here. Now for the first derivative, good evening. And I have plus 15 f of s equals 0. So that last one is we are transforming function x, right? You see that x of t is unknown. Maybe I should I specify that? I guess. X of t is unknown. So that's what we are looking for, right, when we solve differential equation. Guys, look what you got. You got some simple algebraic equation. What do you have? You have s squared f of s minus 2s minus 3 plus 8s f of s minus 16 minus plus 15 f of s equal to 0. Your job is to make fs equal everything else, and then later when we learn how to inverse Laplace it, it would give you an answer. So now you keep, this is like, you know, implicit differentiation. Keep all the dy dx terms on the left. Now you keep all fs terms on the left, everything else on the right, and then divide through. So what do I have? I have s squared f of s plus 8s f of s plus 15 f of s is equal to, and everything else goes on the other side. So I have this negative 2s becomes positive 2s. Now minus 3 minus 16 is positive 19 on this side, right? Because minus 3 minus 16 is minus 19, goes to the other side, becomes positive 19. Now factor out fs, and you're left with s squared plus 8s plus 15 equals to 2s plus 19. And finally get f of s alone. I hope you see that we just did basic algebra, nothing advanced. Yeah, is it cumbersome and annoying? Sure, I'll give you that. But as you can see, I obtained the Laplace transform and I solved it. This is a solution in the frequency domain. I need to learn how to do inverse Laplace, and when I learn the block, which is called inverse Laplace, I will get back x of t. Because remember what this f of s is. F of s is the Laplace transform of x of t. And x of t is what you are looking for. So later, when we do the inverse Laplace, you would see that you have a Laplace of x of t, which is what you are looking for, right, is equal to this 2s plus 19 over s squared plus 8s plus 15, and you will hit both sides with the inverse Laplace. They cancel on this side, and you get your x of t equal, and over here you get whatever the whatever the inverse Laplace gives you. We are not there yet, so I can't do that piece. But I just gave you the outline for solving differential equations using Laplace 100%. Even though we didn't cover all the aspects of it, I told you everything you need to know about it, and then we will cover the rest of the pieces. So let's go back to the original problem. I have initial value problem because these two initial conditions are given. That's why it's called initial value problem. And we know also by looking at the formulas that if we don't have those given, we actually can't even set up the problem, because you will not have these pieces. So Laplace, that's the deficiency of Laplace in comparison to stuff we did before, right? If you don't have initial conditions, you are still fine to do constant coefficients and undetermined stuff and variation of parameters. You were able to do linear equation and multiplying and exact equations, multiplying factor. You were able to do everything so far. And power series as well, right? And now in Laplace, oh, it's so easy to work with Laplace, and you have tables, and you have all these cool features. But, right, there's no free lunch. If you don't have these two, you cannot do Laplace. Now, the cool thing for application is, yeah, those are actually present. Because if I'm tossing an object, this is going to be at time 0, I toss that object from 2 feet height, or 2 meters, right? 2 meters. It was about 2 feet to go like this, but now, 2 meters. Put it in meters, so here it is, 2 meters, right? So I'm throwing it from this height. This is where the object is. So that's the first initial condition. The second initial condition says, what is the speed? Which is something you also can measure, right? Because if I have the grid on that wall and the camera is right there and I throw this, you see that it starts at 2 and then the grid will tell you what's the speed. So these two you get experimentally. Remember the chicken and stuff that you were supposed to bake, right? You're supposed to, within 30 minutes, well, at 30-minute mark, you're supposed to stick the thermometer. That thermometer is giving you this. It's giving you initial condition. And then you can solve that problem, right? When you can solve differential equation. So now, we get the initial value problem. It happened to be constant coefficients and all of that cool stuff. And then you have two initial conditions. Now, you memorize the formula for transforming the second derivative. Voila, right there. And then the first derivative, right there. And then 15x at the end is just 15 times, right? You have to, I'll put this on the board as the key point, right? So you can stare at it at all times. What I'm writing on the board is that Laplace transform of f of t is f of s. So Laplace transform of f of t is f of s, which means that f of t, which is a solution in a time domain, in the world that you have your problem, right, given in. So f of t is the solution for the equation that it's posed. F of s is its analog solution, but that one is in Laplace world, in a frequency world. Cool. So as you can see, when you transform this equation, the equation that you get contains solution immediately, right? This f of s, that's a solution. It's solution in frequency domain, but it's a solution to the differential equation. So the first line that you write is already a solution line. And then you massage this a little bit, right, to get f of s, stop, get f of s equal to everything else, right? And that's a solution. Now that solution is given in Laplace world. And you are going to hit that with Inverse Laplace, right, which we didn't learn yet. So Laplace -1, and that's going to give you your f of t or x of t or y of t, whatever you called it earlier. And problem is solved. How much did we integrate? 0. How much did we differentiate? 0. Right? The only thing that we did was algebra to put these terms together into, right, the solution state. The reason why I have here blah as a solution is because we haven't covered the inverse Laplace, so we don't know what we get. But you see that the solution, which is x of t, is actually the one that we get. Perfect. All right, so now it is time for us to learn how to inverse Laplace, right? How to do inverse Laplace to actually get the solution out of here. So now what I'm going to do, I'm going to put a title inverse Laplace. And then I'm going to continue working on my problem from before. So I have 2s plus 19, sorry, f of s is equal to 2s minus 19 over s squared plus 8s plus 15. Yeah, I hate these s's, you know, it's the same as 5, so deal with it, all right? Now, the way we do inverse Laplace is the same thing we did with derivatives and integrals, right? You learned that the derivative of sine is cosine, and then you use the same thing for integral, where you said the integral of cosine is sine, because you read the derivative backwards. Maybe I should write that. So when you learn the differentiation in calculus 1, you learned that the derivative of sine x is cosine x. And that led later in the same course to integrals where you read this line backwards, which means integral of cosine x dx was sine x plus c. So you didn't learn the new table, new chart or something like that. You just took the one that you know from derivatives and read it backwards. So you know that the integral of secant squared is tangent, right? Hopefully. You know that the integral of 1 over x dx is ln absolute x plus c and so on, right? Because you know derivatives. Now, for inverse Laplace, you have to do the same thing. If your Laplace transform of e to the 3t gives you 1 over s minus 3, then inverse Laplace of 1 over s minus 3 has to give you e to the 3t. Do we see that? So inverse Laplace, you are not learning the new chart, and you are not getting a new chart for Laplace. You're not getting 2 charts for your test. You are only getting the Laplace transform chart, and then you need to know for inverse, you look the other way. Yeah. It's going to be epic, yes. We might have different definitions for epic, but yeah.
Epic is power series, infinite series. That's epic. Partial fractions is boring.
Yeah.
Sure.
Okay.
Yeah, it's okay. Just all right, fine. All right. Well, I'll have to go with you on that one then. So now, in order for us to solve this problem, we realize, right, that the solution to our previous problem is we have a Laplace transform of x of t, right, which is what we're looking for, that's our f of s, is equal to this 2s minus 19 divided by s squared plus 8s plus 15. Just make sure that that's, so all plus, see? I started putting minus signs, and then, yeah. There we go. Nice. Now, the oldest trick in a book, when you have a fraction, and you have addition and subtraction on top, is to separate. But you see that you are getting this on the bottom, and that doesn't match anything in a chart, so in this particular case, separation doesn't help. So, what else can you do? Well, how about we try and use partial fraction decomposition to see what we get if we are to, but then can we factor this, right? So this is 2s plus 19 divided by, s plus 3, s plus 5. Nice. Now, I hope that this, in everyone's case in this classroom, screams partial fraction decomposition, right? So, here we go. We have two linear terms, therefore a over s plus 3 plus b over s plus 5 is equal to 2s plus 19 over s plus 3, s plus 5. Now cross multiply, so as plus 5a, oh, it's going to be epic with this s and 5 like everywhere, plus bs plus 3b equals to 2s plus 19. We are not changing letters, so deal with that. Now, partial fraction decomposition has a plus b, s, plus 5a plus 3b is equal to 2s plus 19. We combine the terms, right, of s together to give us a plus b equals to 2. And then constant term with a constant term where 5a plus 3b is 19. Solve this system with whatever witchcraft you can. Whether it's matrix, substitution, elimination, if you, I don't know, throw the bones in the something and look into it, whatever you do, beans or whatever it goes, I don't know. I generally use substitution. So whatever gets you to calculate the value for a and b. Sorry, I generally do elimination, sorry, not substitution. So I multiply the top equation by -3, and then I add equations, and that will give me immediately. So I get 2a, right, because 5a minus 3a is 2a. B's die. And then I have -6, 19 minus 6 is 13. Sheesh, you had to be a fraction. So a is 13 halves. So if a is 13 halves, right, we can compute b by plugging in 13 halves. So b is going to be 2 minus 13 halves. So that's -9 halves. So what do I have? I have 13 halves over s plus 3 plus negative 9/2 over s plus 5. So this is what my f of s is now. I transformed it, right? I transformed it. And this is the time when you go into your chart and you say, what does this look like? What is this? E, right? If you carefully observe this 13 over 2 s plus 3, hopefully you see that you can write 13/2 times 1 over s plus 3. And the inverse Laplace for this puppy here is e to the 3t. Right? So this becomes 13/2 e to the 3t. So, oh, actually, I don't know why I did this on the side. I should do it as a step over here. So further, I can actually now replace this as a Laplace transform of f of x of t is equal to 13/2 of 1 over s plus 3 minus 9/2 of 1 over s minus plus 5. And then when I hit both sides with the inverse Laplace, over here, inverse Laplace kills off the Laplace, and you get x of t, which is what you're looking for. And on the right-hand side, as I said, the table shows over here that this is e to the 3t, and the table shows here that this is e to the 5t. So what do you get? You get 13/2 e to the 3t minus 9/2 e to the 5t. Now, you're not going to use the sledgehammer for a problem that it's easy to do, in a different way. This was a constant coefficient problem, right? So you can just do characteristic equation and you're done. But then you have to go and chase the conditions and make sure you get 13/2 and negative 9/2. So Laplace is used on spicier examples, obviously, not on just what we have here in terms of constant coefficients. So we're going to take a look at those. So now you have the answer, and observe that your C1 and C2, which you had to sweat for, right, in 2.1 or whatever we did this, it's already given, right? Because you remember that you fed initial conditions in original equation in the setup? That's why the 13/2 and 9/2 are already given. You don't get to compute things. But again, the downside to the whole procedure of Laplace is that if you don't have initial conditions, you don't get to do a Laplace at all. I know. Heartbreaking, right? Now, I'm going to pick another problem, solve one more. Yeah, this looks cool. X double prime plus 4x is equal to cosine t, where x of 0 equals x prime of 0 equals 0. What do we do to solve this problem? Variation of parameters. Can we do undetermined coefficients? Yeah, we can do that too, right?
Sounded so disappointed.
How long?
Is it because of the 4 you could do the coefficient?
No, you can do them because you have the forcing on this side. So it's and both of them work. Now, how much work do we put into those? I can only see the pain, right? But let's convert this in the Laplace world and see what we get. So we are moving from the time domain into frequency domain, right? Remember, x of t here, x of t, time domain. When you transform it into Laplace world, it becomes frequency domain in terms of s. So now what do we have? We memorized that the second derivative transforms into s squared f of s minus s times f of 0 minus f prime of 0. But hold on, these two are zeros, right? Look at that. Initial condition equal to 0. Yay. And then plus 4f of s, right? When you transform x of t, you get f of s equal to a cosine on this side. Now, inverse Laplace of cosine is going to be the same as inverse Laplace for the sine, except one of them has a and one of them has k on the top. Now, if you're not memorizing these things for Laplace transforms, you are going to take a look at the cover of your book, or you're going to take a look at whatever Laplace transform table you have. So the cosine needs to be a over, s over, not a, over s squared plus k squared, as I have foreseen, right? So k is, did I copy this right? Yeah, I did. So k is 1, so therefore we have s over s squared plus 1, which is k squared, so it's 1. So when I factor out f of s on the left-hand side, in parentheses I have s squared plus 4, and on the right-hand side I have s over s squared plus 1. So now to get f of s alone, cheap trick would be to multiply both sides by 1 over s squared plus 4, right? And what you get is that f of s is equal to s over s squared plus 1 times s squared plus 4.
Quick question. Why was the k 1 again? Because you used
K,
cosine k of t?
cosine kt, yes.
Right. And so that came s over s squared plus k squared.
Yes, and k was 1, so 1 squared is 1.
Oh, this k.
K is 1 because when you look at, it's 1 in front of t, yes. All right. What now? Yay. And now this time partial fraction decomposition has a bit spicier terms, right? We have two unfactorable quadratics, which means as plus b, and then for the other one, cs plus d. Hello, Calc 2, right? So, as plus b divided by s squared plus 1 plus cs plus d over s squared plus 4. This is the time when you turn your notebook landscape and start writing. So, cross multiply to get 16 terms over here, right? Oh yeah, welcome to Differential. How? What do you mean use the cal for what?
Matrix.
Oh, you are entering the matrix, huh? All right, Neil. Let's see how that works for you. So as cubed.
Oh, after when you do this step.
Oh, yes, yes. So as cubed plus 4as plus bs squared plus b4, 4b. Plus cs cubed plus ds squared plus cs plus d. I'm tired. That's it. I'll see you all next week. Thank you. Yeah. So now we have a plus c s cubed plus b plus d s squared plus 4a plus c times s and plus 4b plus d. All of that equals 0s cubed plus 0s squared plus single s plus 0. The reason why I put all of these 0 terms in as placeholders because we have to put these guys together. So here's my red equation. It says a plus c is 0. Here's my blue equation. B plus D is 0. Here's my green equation. 4a plus c is s. Is 1, sorry. 1. And here's the purple equation. 4b plus d is 0. Nice. Now this is why you don't need matrix for this one. If you know they're coupled. You see that? So I actually have two sets of two equations with two unknowns. I hope you all see that. So the first equation up here, the red one, we have to solve this system. The red equation tells us that a is equal to negative c, and we can plug that in a green equation, so we get 4 times negative c plus c is equal to 1. And that's going to be negative 3c equals to 1, from where c is negative 1/3. Which immediately means that a is positive 1/3, because a is equal to negative c. And I got a and c immediately. Now, the second set of equations says that b is equal to negative d. And I plug that in here, and I get that they're all 0, but I mean, hopefully you see that, especially if you took linear algebra, you know how the systems work. But is something funny about linear algebra? Yes? Okay. So negative 4d plus d is equal to 0, from where you see that d is 0 and then immediately b is 0. So now, b and d are zeros, a and c survive. So I have 1/3 divided by 1/3 s. 1/3 s divided by s squared plus 1. Plus negative 1/3 s. Remember that b is dead, so c is again 1 in front of s. S squared plus 4. Yeah. So this is our f of s, right? And now I'm going to write this f of s as the Laplace transform of my x of t is equal to, and then kick these coefficients, constants in front. So I have 1/3 s over s squared plus 1 minus 1/3 s over s squared plus 4. I am going to hit both sides with the inverse Laplace. The inverse Laplace kills off Laplace. We get x of t. And now is the time to enjoy the other side. 1/3 gets copied. And now what is s over s squared plus 1? Cosine 1t. So just cosine t. Nice. Minus 1/3. And what is s over s squared plus 4? Cosine 2t. Cosine 2t, because you're remembering that this puppy over here is k squared. And if k squared is 4, then k must be 2.
What about negative 2? That was a little question. I'm sorry to make it sound so. What about negative 2?
What kind of function is cosine?
Yay.
All right, so the next question. Right?
Okay, what if it was sine?
So, k is always positive. K is always positive because remember where it comes from. It comes from sine kt and cosine kt. Now, if you say that the input was a negative number here, right, then you would have sine of negative 3t, and that minus would float in front, and you would actually, you would not be dealing with that minus sign, and you will not get it in the end. For cosine, its even function, it just dies right off the bat. Good question. I would say, I don't know, partial fraction decomposition, undetermined coefficients, variation of parameters. I don't know, but I don't get to integrate or differentiate, right? We get to go back to 8th grade. I mean, right?
It's like partial fractions without the fun.
I know, like the ancient history, right? But I don't know. I mean, have I ever used this in application? Hell no, I'm Mathematica, right? But at least, you know what gives you, as someone is passing a hallway and say, hey, how are you, what's new? Napkin and start writing it down. Laplace transform. What?
You also do the integral test on that.
You have no idea how powerful it is. That's it. Let's say you go ice skating and someone says, okay, can I come along? I say, can you do Laplace transforms? No, you can't.
But if they're useless, why would I need somebody who can do it? I know, right?
It's the fastest way to ditch someone you don't like. Think. I just gave you the example what you need Laplace for.
Oh, in case you don't have Mathematica.
I mean, come on. Look at the benefits of the whole thing. Ooh, sheesh. It's not gonna be fun.
You need something with a lot of friction. You also like toilet paper. You also like toilet paper. You do a project, napkins.
All right. So here's one for you to enjoy. Way too much fun with Laplace transforms.
They just smoke pot every time they come to the equations, so.
He just said you are too happy. In his own unique way. Come on, use the Laplace. Start writing. Don't sit there like a bump on a lot. Did I do this correctly?
you didn't plug in the.
How do you get
I haven't plugged anything in yet. It was just, I just expanded. Yes. Well, the whole thing over here will be replaced by 2 because that's what it's equal to, right? Maybe I should call these, instead of using f's, maybe I should just call them x's because that's what they are. It's x of 0, x prime of 0, x of 0. Better? That's the Laplace transform. Like, look at the book. Yep. So now we plug stuff in. This one dies. This one dies. Is this what everyone has so far? Now we have to combine these two before we bring over more stuff. So this is going to be 1 plus 2s squared over s squared. And now we bring the rest. So f of s is equal to 1 plus 2s squared over s squared times, if we factor this, is s plus 1, s plus 2, right? What happened?
I thought that there was a 5 in front of x prime, so I'm like, it's plus 2 hard x.
Oh, it's s, yeah.
Yeah. No, I thought you wrote a 5. I mean, before x prime at the very top. Instead of 3.
That's a 3.
Yeah, and that one dies because minus 3 and minus s.
Which one?
What else did I miss there?
This one, see that?
No, when you crossed out that one and that one, why did we, what else did we miss there? You said it died.
Yeah, because of this.
Oh,
It's equal to 0.
in the condition.
Yep, 0 in the condition. 0 in the condition. Oh, you're not planning to graduate anymore? That's it? You've seen Laplace transform and that's kissed your graduation goodbye? Nah, there's nothing that 16 hours on Sunday can't solve. Come on.
Yeah.
What happened?
It's supposed to take a break on that day. It's got Sabbath.
Save your prayers. God is not here with us now.
After
Just Laplace.
2, that's it.
Just Laplace.
When he gives up and it's on your own. You need to do your you have to do your homework on Sunday now.
Yeah. Well, wow. Actually, it was Laplace who was summoned before Napoleon to show up his Laplace equation. And Napoleon asked him, how does God factor into this? And he said, sir, I didn't need that hypothesis. Yeah. Wow. Well, that...
It's in full circle.
Look, you just Google it now. Laplace Napoleon. That's... He's got it, don't worry about it. The rest of the problem. 2 O's. Google, Google, Google. I hope you all have the same setup for the partial fraction decomposition.
They are different coefficients. The S used.
Yes, that's the linear, s plus 0. So it's a repeated linear, which means s squared. And then a single s plus 1, single s plus 2.
Okay, what am I looking at? Napoleon Laplace episode. Here's sine of Laplace. Oh, there's no need for God as the same.
Where did I get what?
There it is.
Yeah.
There it is.
Yeah.
So if it's like
Here's sine Marquis de Laplace.
So the rule for s plus or s minus c, whatever x, I don't know. I'm writing the rule for partial fraction decomposition. So when you have a linear repeated, so it's a square. Did you find it?
I got it. Says Laplace presents his definitive work on the properties of the solar system to Napoleon. Napoleon, liking to embarrass people, asked Laplace if it was true that there was no mention of the solar system's creator, i.e. God. In his Opus Magus, Laplace, on his occasion, at least, was not obsequious and replied, I had no need of the hypothesis. This is essentially the simplicity argument discussed in the previous blog, but stated very clearly.
Yeah. So when c is equal to 0, right, it reduces to what we have over here. You just have x squared, which is s squared, and then it gets these two, right? The one without and one with square.
But I got meaning on my side. Meaning on my side. People have got plus.
Well, actually, back in the day, there was a lot of scientists that felt pressured to, be in the faith because they wouldn't be allowed to continue the research otherwise.
Which one? Yes, partial fraction decomposition. Guys, just focus on this one now. Leave the Laplace for... Oh no, actually do the Laplace here. So Calc 2, you have repeated linear, another linear, another linear. So you have 4 of these guys now. And so let's cross multiply. So A needs to be multiplied by, when you FOIL s plus 1, s plus 2, and then times another s, you get as cubed plus 3as squared plus 2as. 2as. So that's for the first one. Plus, now b just needs to go with this, so bs squared plus 3bs plus 2 b. Now c needs to be multiplied by s squared times s plus 2, so that's s cubed plus 2s squared. So plus c s cubed plus 2c s squared plus, now d has to have these two, so that's ds cubed plus ds squared. Yeah, I'm out. That's it then. Good. 1 plus 2s squared. This is not h, this is a plus. Now, put all the cubes together, so that's a plus c plus d. Oh, really? B did not? Oh, no, it didn't. Good. S cubed 3a plus b plus 2c plus d for s squared plus single s's 2a exactly plus 3b that's times s and plus the single ones 2b. Ooh. So what do I have? I have 0s cubed plus 2s squared plus 0s plus 1. Nice. The red equation plus, no, we do this the good old, use the force way. 3a plus b plus 2c plus d equals to 2. Green equation. 2a plus 3b. Oh, this is easy. This is really easy, guys. We're lucky again. Look, we have equation 2b equals to 1. b is a half. And you immediately bring it up, you have your a. So b is a half. Now plug that into green. So you have 2a is equal to negative 3 halves. So a is negative 3/4. Who comes up with these numbers? And now I have a, which is negative 3/4. So c plus d is 3/4. I have 2c plus d is equal to, and now a and b together. So I have negative positive 9/4 on the right hand side, and then b was positive, so minus a half. So that's 2/4, so that's 7/4. Let's say it's good, all right? So now we subtract equations, and I'll do bottom one minus the top one. So c is equal to d is die, and 1. And if c is 1, d must be negative 1/4. Done deal. So, our f of s is equal to, we have a, which is negative 3/4, times 1/s, plus b, which is 1/2, times 1/s squared, plus c, which is 1 over s plus 1, and then finally negative 1/4, 1 over s plus 2. We hit both sides with inverse Laplace. Yeah. And now we have x of t, which is a solution, right? Inverse Laplace and Laplace cancel. 1 over s. That's 1. So just 3/4. Inverse Laplace of 1 over s is just number 1. Plus 1/2, 1 over s squared is t. Plus 1 over s plus 1 is e to the t. No, it's e to the negative t, because it's a plus over here. And then minus 1/4 e to the negative 2 t. So let's take a look one more time. The Laplace transform of e to the at is 1 over s minus a. So, if I have Laplace transform of e to some t, where I have 1 over s plus 2, let's say, then this is 1 over s minus negative 2, from where we conclude that a is negative 2, and that's why we fill the negative 2 up there. I don't have a microphone, I will just...
Is this also work for
Oh no. Constant, yes.
And a forcing term? Is that forcing term always have to do this?
Where?
On the right side. Or it can be 0 on the right.
You did so.
Yeah.
Cool, right? You have something to do the entire weekend. Play with the Laplace transform. Now, what else is there in this section? No, you don't have to worry about it. So, remember your last exam, there was a question which gave you the mass and the spring constant and dampening? Yeah. That's this. This solves that problem. So if you want to practice a problem that is a possible problem for your next exam, as you're going to go home and dig up your exam 1 and you're going to find the word problem, I believe number 4 or something, or 5, whatever's the word problem with 6, and you're just going to solve that problem using Laplace now, because this is what your next, if you pick to have next exam, that's what's on it. And that's going to be, again, a simpler, one of the simplest possible Laplace transforms, because you guys are having the this as a constant coefficient, right? And it will be constant coefficient, and then there is nothing on the other side. And you solved it with the constant coefficient, so you know what the answer is on your exam. So now you just need to get the same answer using Laplace. There was something else that I want to mention. Oh yes, there are these very interesting examples here that have systems of equations. So let's take a look and outline one of those. For instance, problem number 12 says x prime is x plus 2 y, and y prime is x plus e to the negative t. x0 is the same as y0 is equal to 0. Yay, we have system of differential equations. Who's excited? Now, you're looking at this, and you say, do I have to do it right? No. There's a very simple, cheap trick where you have your x prime equals to x plus 2y, and you differentiate that equation in terms of t. What you obtain is x double prime is equal to x prime plus 2y prime. What we did is we took a system of two first-order differential equations that had x and a y and combined it into a one second-order differential equation. I mean, if this is not cool to you, you have no emotion. I mean, towards mathematics. Maybe you...
No, just no emotion.
Yeah, you're dead inside. So, the whole thing over here now, as you can see, is second-order equation. You are going to have your x double prime minus x prime minus 2x is equal to 2e to the negative t stays on the right. And you just now unleash Laplace. What happened? Yeah.
You plug in, you differentiated first and then you plug in one again? You plugged in one equation into the other?
Yeah, because you see this is x prime and then 2y. When I differentiate that, I get x double prime plus x prime plus 2y prime. Now I know what y prime is. So instead of this y prime, I plug in what y prime is from the second equation, and now distribute 2 and just manipulate the terms. See that? So you can now go home and you can just finish off this problem as well, and practice a whole bunch of these. So Laplace, you know, when you get a hang of it, you'll see that Laplace is extremely easy to deal with because it's pattern, pattern, pattern. There's not too much thinking involved. Just keep pounding on it. And the interesting thing is that they explain into more detail the partial fraction decomposition at the beginning of 4.3. So if you are lacking skills from Calc 2, the definitions for partial fraction decomposition are in here. But you can also find my partial fraction decomposition YouTube stuff or someone else's with a better accent, and then you can review that as well. Let me just kill a buy stream.